into the heavens with awe and wonder. For them, the night sky told great stories of gods and heroes. Over time, as myth and legend gave way to science, we slowly started to reveal the true nature of the cosmos. But recently, we discovered a problem that really does need to be solved.
The universe is getting bigger. Space itself is expanding. Astronomers have known this for a while, and for the last few decades, they've been trying to measure how fast this expansion is proceeding. Until a few years ago, we thought we had it all sorted.
But now, conflicting results have divided the scientific community.
It's a real conundrum, it's a puzzle to try to work out.
I'm getting to the point where I'm saying something interesting is going on.
We're going to meet the scientists trying to answer this question that's key to the past, present, and future of our universe.
It might be telling us that there's something that we don't understand about the universe so far. It might be pointing us to something really new.
Tonight, we're going to explore this fundamental mystery. Welcome to the Sky at Night.
This film is an actual record of modern astronomy, for our world's origin and destiny is linked with the atomic mysteries of distant stars. Dr. Edwin Hubble, on a movable platform, lines up the massive telescope as he begins a cold night's work.
In the 1920s, Edwin Hubble made two revolutionary discoveries.
As the lights go out, he pulls the slide, and the huge instrument makes a time exposure of the selected object, the great spiral nebula in Andromeda.
The first was that objects like this were actually entire galaxies outside our Milky Way.
The study of these so-called spiral nebulae has proved that they are actually vast island universes, billions of miles in diameter and similar to our own galaxy.
The second was that these distant galaxies were moving away from us. It appeared the universe was expanding. Working at the speed of these galaxies was relatively easy. The faster an object moves away from us, the redder the light. This is known as the redshift. But working at the distance to them was the hard part, and Hubble needed both the speed and the distance to work out the state of the universe. Hubble had an ingenious solution. He used stars called Cepheid variables that pulse at a frequency directly related to their brightness. By counting the time between pulses, he could tell their true intrinsic brightness, and he could estimate how far away they were. Hubble spotted these beacons in other galaxies at vast distances. By cataloguing each galaxy's speed and distance, Hubble was able to work out the rate of expansion of the universe, and this was later known as the Hubble constant. That was back in 1929, and his result was quite controversial. By the late 20th century, a new way of looking at the universe and a new Hubble promised to settle the debate.
3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
The telescope's released. Okay, thank you.
The Hubble Space Telescope.
Go ahead, Charlie.
In the 1990s, Wendy Friedman led a team to use the Hubble Space Telescope for one of the most ambitious experiments ever attempted. Building on Edwin Hubble's catalogue of galaxies, but with instruments able to give a far more accurate measurement of the expansion rate of the universe. Hi Wendy, thanks so much for tuning in. When you started your work in the 1990s, what was the consensus on the Hubble constant?
There was no consensus. In fact, there was a debate, a rather heated debate about the value. It was not a coincidence that the Hubble Space Telescope was used to measure the Hubble constant. In fact, one of the primary reasons for building the Hubble telescope was to resolve this debate. It was one of the most important outstanding questions. How fast is our universe expanding? So that's why when the Hubble was launched, we were excited about being able to resolve the controversy.
How much better were the results that you got compared with Edwin Hubble's?
In the case of measuring the Hubble constant, one of the most accurate means we have available is to measure a kind of a star. It's called a Cepheid variable. And it turns out that the rate at which they're changing in their brightness is directly related to how bright the star is. And so if we can measure these stars nearby, near to the sun, and use geometrical techniques, literally high school geometry, to measure absolutely how far away those stars are, then we can compare them with stars that are more distant and determine how far away they are. It was the method that Hubble used, it's a method that we still use, and it's one of the most accurate means that astronomers have for measuring the distances to galaxies. Primarily, it was the first time that astronomers could make measurements of these Cepheid variable stars from above the Earth's atmosphere. We were able to measure the distances to a couple of dozen galaxies very accurately and then determine how fast the universe is expanding, or the Hubble constant, to very high precision and accuracy for the first time. The value that we measured for the Hubble constant using the Hubble Space Telescope as part of the key project was 72. And we resolved the debate that had been going on for decades.
So when you got the result, did you think it was case closed, sort of job done?
I did not expect to still be working on the Hubble constant in 2019.
Wendy's team, using the Hubble telescope, settled on the number 72 for the speed of expansion of the universe. But what does 72 actually mean? If you want to work out how fast space is expanding, you should start with a standard amount of space. We can use a megaparsec, which is a little bit further than the distance to the Andromeda galaxy. And if you watch that carefully, you'll see that that megaparsec of space gets about 72 kilometers longer every second, which isn't very much. And that's why it's hard to notice that the universe is expanding as you go about your daily life. In 2013, new measurements gave us another way to clock the cosmic expansion speed, looking not at nearby galaxies, but at the oldest light of all, the cosmic microwave background. Hiranya Pires is one of the cosmologists using a satellite called Planck to map this ancient light. So you've been studying the cosmic microwave background. What is that?
The cosmic microwave background is the afterglow of the Big Bang. So the early universe was very hot and dense. And as the universe expanded, it cooled, and eventually atoms formed. And so at that time, the radiation was just kind of released. And for the intervening 13 point something billion years, that light has been kind of free-flowing through the universe.
So you've got this ancient light hitting your satellite. What does it look like?
So most of the time, when you look at the cosmic microwave background, you see just a sea of radiation in every direction. But if you look at it in fine detail, like Planck can, because it's so sensitive, you see that there are tiny ripples in this light. It's a kind of map of how the density of the universe varied at very early times. The tiny, tiny lumps in the early universe is what grew into all the structures we see today. So you see patterns in the cosmic microwave background, in the little fluctuations, and at the same time you can go out and look at the distribution of galaxies in large surveys. These structures today are not randomly distributed through the universe. They come in like streams and long filaments of structure, and you can map that pattern back to the one that you see in the cosmic microwave background because they're made by the same process.
So we've got the early universe as seen in the microwave background, and we've got today's universe. How do you measure the expansion?
When you see this lumpy pattern, there are these hotter and colder spots on the sky. They don't come in all sizes. You see that it has a particular scale.
So that's a feature that you can measure in the microwave background.
That size is a ruler as we see it now. And you know the size of the ruler as it was in the very early universe.
Hrania measures the expansion by comparing the cosmic background radiation with her models of the early universe, creating a kind of cosmic ruler or yardstick.
The relation between those sizes allows us to tell how long the universe has expanded, and therefore what is its age, which is one of the age-old questions that people have been asking. We can work out the age of the universe. And as a byproduct, it tells you how fast it's expanding now.
What did making those measurements with Planck tell you?
So Planck gets about 67 in the unit we care about.
Hrania and her colleagues got 67 kilometers per second per megaparsec, not 72 as expected. It may not sound like much, but in this kind of research, it's hugely significant.
It was surprising because the preceding years there had been an expectation based on other measurements. What matters is not the actual number, but the error bar as well. And the error bars are very small, to the point that actually that difference does matter. It tells you that there really is a significant tension between them.
You tempted to say that the others are wrong?
Not in a pejorative sense, but because anyone who takes complicated data and analyzes it always worries about something you might have misunderstood about the data. So there were a number of questions raised about complicated astrophysics that could be going on in the other data set.
Hrania and her colleagues had a result that didn't match the original measurements, and so it was back to the astronomers. And in 2016, things got even more complicated. Here at Johns Hopkins University in Baltimore, Adam Rees and his team have been trying to match the precision of Hrania's result using data closer to home. If both teams could just settle on the same speed, then all will be well with the universe again. Well, we're 5 years into the story, and this discrepancy hasn't gone away.
I came in with my own skepticisms. Could there be a problem in those early universe measurements? They say, this is the way the universe is going, we understand things, we think, and so today, here's how fast it'll be expanding. And yet, do we really understand that? Because it involves understanding some very mysterious parts of the universe, like dark matter, dark energy, gravity, the state of particles in the universe. So we thought, we should really go out and measure that rate as well as we can. In fact, measure it to comparable precision to that prediction. We actually go out and measure how fast the universe is expanding much more directly.
When I said to people that I was going to talk to you, everyone said the same thing, type 1a supernovae, that's what you're known for. So what are type 1a supernovae and why are they useful?
A supernova is the explosion of a star, and a type 1a supernova is a particular class. When you get one of these explosions, they're as bright as 10 billion times the luminosity of the sun.
So that's about the brightness of a galaxy.
Yeah, it certainly rivals a galaxy. What's particularly important is that they are just about the brightest cosmic lamppost or lighthouse that we know of, and so you could see them up to about halfway or 3/4 of the way back to the Big Bang. And so they're very good for measuring faraway distances.
So you spot supernovae at different distances. And this is the work that led to you eventually winning the Nobel Prize, but you didn't stop, you kept going and started to compare supernovae and the results from Cepheids. What did that tell us?
What we often don't know is what is the absolute distance. And so what it would take to do that, find galaxies that had nearby type 1a supernovae, and then you go and you look for the Cepheids in those galaxies. Then we observe the evolution, the time evolution of the supernova so that we can measure its distance, producing this kind of connective rung in the distance ladder.
You measure your Cepheids, you measure your type 1a supernovae, you put it all into the statistical box and shake it, and you get a number out for the expansion rate for the Hubble constant.
That's right.
So what results do you get?
We get an answer that is more than most of us expected.
Adam's results in 2016 were even further away from the cosmologist's value of 67. According to him, the universe was expanding even faster than had been expected, at over 73 kilometers per second per megaparsec. So when you first got this result, the idea that the Hubble constant was larger than expected, did people believe you?
There was a lot of skepticism initially, particularly from what I would say the people who work on the early universe end of this.
First of all, could you not just be wrong? Could you have made a mistake in the calculation? Are you sure?
The way we like to talk about discrepancies usually is, what are the odds that I would see that discrepancy just by chance, just by, bad luck? It's sort of like the difference between saying, when you play the lottery, did you win because you're lucky or because you have ESP and you're able to predict the number?
Or you bought enough tickets.
That's right, or you bought enough tickets. So in this case, we are at odds of about probably 1 in 10,000, maybe 1 in 100,000, that you would get this kind of result just by chance. And so we are getting to the point where it's very difficult to say, oh, that's just bad luck. So the fact is, at this point, it wouldn't just be an error in a measurement. It would really be more like a conspiracy of errors. You would have to have multiple independent errors conspiring in a way to keep giving you the wrong answer.
What will you do next? What's the next step?
So I'm most interested in increasing the robustness of these measurements as well as improving the precision.
In normal language, that means doing a better job,
yes,
right?
Do a better accuracy and precision. And we're saying, what could possibly be wrong in this measurement chain, and trying to reproduce any aspect we could think of.
So you're now trying to prove yourself wrong, sort of.
Correct, yes, before somebody else does.
Yeah. So we're in an apparently absurd situation. Adam and his team think that their measurements are right. Haranya's team think that they're right. And both teams even think the others are doing a good job, and yet the results disagree.
So what we have are two very different ways of trying to answer the same question. How fast is the universe expanding? It all comes down to how well we are able to measure vast cosmic distances. Close to home, it's easy to get an accurate measurement of both speed and distance. We can bounce radio waves of objects. We can look at planets and moons moving across the night sky. But as we move further out into the cosmos, we need to get a little more creative. Enter the cosmic distance ladder, built from beacons of known brightness, like Cepheid variable stars. This is a Cepheid variable that sits within our Milky Way galaxy. Now, Cepheid variables pulse with a frequency which is directly related to their intrinsic brightness. So if you can see one of these, you can work out how far away it is. And this gives us the first rung of the cosmic distance ladder. Now we're moving out to the next rung of the ladder, nearby galaxies. Now we get Cepheid variables in these. And if we can spot these, we can work out the distance relatively easily. But to go beyond here, we need to make use of a much rarer cosmic candle. Out here, we're in the realm of the distant galaxies. Now, unfortunately, Cepheid variables out here aren't bright enough to be spotted from Earth. But we do get the occasional supernova. Now, if we calibrated the brightness of the supernova correctly at rung 2, it means that we can use that same brightness out here to measure the distance to rung 3. That's the way astronomers have been doing things. But cosmologists are approaching the problem from the opposite end of the cosmos. Out here, at the most distant point of the observable universe, we have this, the cosmic microwave background, the afterglow of the Big Bang. The variation that we see in this map gives us the seeds of the structure we see in the modern-day universe. The distance between peaks gives us something called the cosmic yardstick, another handy way of measuring distance. Comparing this ancient map with the distribution of galaxy clusters that we see in the modern universe gives cosmologists the opportunity to measure the expansion of the universe since the Big Bang. While it's incredibly impressive that two completely independent methods have given answers that are so close, within 10% of each other, the fact that they don't agree is troubling.
The question as to how fast the universe is expanding is one of the biggest mysteries in astronomy, and it's one which is normally reserved for the largest and most advanced observatories in the world. But with a bit of luck and some clear skies, amateurs can catch a glimpse of some of the night sky objects involved. Tonight, the Baker Street Irregular Astronomers are descending on Regent's Park for their 100th meeting. They were formed in 2010 with the goal of showing Londoners the wonders of the night sky above the city lights. You might think that central London has to be pretty much the worst place in the country to be doing astronomy because of the light pollution. But then again, you might be surprised at what these astronomers can do. I'm looking for somebody taking a picture of a galaxy, and I understand you're the man.
That's right. It's amazing that you can do that in central London.
It's absolutely incredible. I mean, I can see stars up there, but the sky isn't black. It's got a sort of orangey colour.
So what we have in here, you can't quite see it, there's a light pollution filter. So right now we're on the Andromeda Galaxy.
Okay.
Which is...
This is the Andromeda Galaxy
here?
Yeah,
right. So right there,
wow.
that's a picture we just took. It's a 1-minute exposure of the Andromeda Galaxy.
That's got the dust lane running along there, the core, very evident.
And the satellite galaxy down here.
M110.
Yeah, it took us 60 seconds to take that picture.
So have you been looking through London skies at any faint galaxies?
M51, we had to go earlier on.
The Whirlpool Galaxy?
The Whirlpool, yeah.
Yeah, did you get to see any of it?
You could see a faint smudge. There was definitely a galaxy there, but teasing out detail.
That's not bad though. I mean, the skies are a little bit sort of hazy. So any others that you've had a go with?
In the past we had M81.
Oh, okay, the Cigar Galaxy in Ursa Major.
Yeah, the supernova a few years ago.
I remember that, yeah.
Mill Hill.
Right, okay.
Which is about 2 or 3 miles that way.
Yeah.
Discovered it with a little evening. They were meant to be doing some photography, and it was cloudy.
Right.
So the lecturer went, "Oh, there's always M81." Swung over to that, and went, "Wow, that looks slightly strange."
That's classic astronomy, isn't it?
Absolutely. So a few weeks later, we were down here, and there must have been 80 or 90 people that got to see a supernova in a distant galaxy.
That's incredible. What did it actually look like? Could you actually see much detail?
There was definitely structure in the galaxy.
Okay.
You could see the dust lane, and then off to one side was a very distinct star.
Right, okay. The supernova.
The supernova.
That's amazing. There's lots of people around, lots of people queuing for telescopes and looking through telescopes, looking for some galaxies, but I think you're looking for something different.
We've been looking for Cepheid variables.
Ah, right, okay.
And, not always the easiest thing to spot from the skies of central London, but some of the brighter ones do stand out.
Okay.
Delta Cephei being obviously the classic one to look for, and as we all know, a very important star and a very useful benchmark on the scale of the universe.
Of course, the standard candle. Well, this is an incredible gathering. I can hear wows and I can see smiles on faces.
Yeah.
It's just amazing to see so many people so interested in astronomy.
You can teach people things without them realising they've been taught. They go home and they think, I learned something tonight, but it wasn't painful.
And you must be doing something right, because it's not the warmest of nights tonight, and I can see frost forming on your telescope.
Absolutely, yeah, this is unusual.
So even from a light-polluted city like London, it's still possible to get a glimpse of some of the objects which are keeping the brightest minds in astronomy busy.
So there's a debate between astronomers and cosmologists over just how fast the universe is expanding. At least, that's what the observations are telling us. Time to call on a theorist. So, Andrew, we have these two ways of measuring the expansion of the universe. The cosmic background radiation and also astronomy distance measurements. Now, they don't seem to agree. Is that a problem?
In short, yes, it is a problem. We'd like, obviously, these things to agree, but it's a nice problem.
Something to get our teeth into. So if we actually dig down and look at the two different methods, it looks as if there could be mistakes made in the methodology. So for instance, the astronomers, they're doing sort of various measurements, but where do you think they're vulnerable?
It's a very, very difficult measurement to take in terms of the astronomy you have to do. It's building up a sense of where things are in the universe using what we call a distance ladder, and each rung on that ladder is kind of calibrated off the previous rung. So, for example, you need to understand the physics of variable stars, the way that stars actually pulsate and the way that's related to their brightness. That's very complicated physics, and if we are calibrating it slightly wrong, that's the kind of place where we could just run into trouble.
So I suppose if you get a mistake early on, it just gets compounded as you go further and further out?
Absolutely, yes. And any one rung being wrong means that the rest of them are just incorrect.
So the cosmic microwave background, the calculations done with that, what sort of errors could have crept in there?
The cosmic microwave background is leftover light from the very early universe. So if you're going to use it, you need to understand what was going on in the very early universe, and in particular, all of the components. What was the very early universe made of? What are all the different types of particles and so on flying around? If you get that wrong, then you'll be calibrating your understanding of the early universe wrong.
Sounds challenging. But what if it's something else? What if their measurements are actually correct? What else could be happening?
It might be telling us that there's something that we don't understand about the universe so far. It might be pointing us to something really new.
Is one of them correct? Are both of them incorrect? It could come back with a third answer, and then I have no idea where we would be.
And as a scientist, I have to ask myself, is it more likely that we keep making errors in unrelated measurements, or do I have to possibly accept that there is some actual difference here?
What are the candidates? What could be out there that we just don't know about?
Well, the kind of things that would get us excited are if something in the early universe is missing from our current account. So if you had some extra particle in the early universe flying around, that could make the kind of changes that we're talking about. If it's a problem with the late-time universe, then either it's something about the observations we're taking, we just haven't understood the physics of how stars work, for example. Or it could be that the properties of dark energy that we're assuming, so dark energy is this thing that actually seems to be pushing the universe. If the properties of that component of our universe are not quite what we're assuming, then maybe that could account for it as well.
This is really a question of, can we really understand the universe?
It's a real conundrum. It's a puzzle to try to work out.
I think all cosmologists and astronomers are thinking about this problem very, very carefully. And one thing that we can do is try combining our data that we get from telescopes in different, new, creative ways.
The cosmologists and the astronomers are in what I can only describe as a fairly heated debate. Why do they care so much?
It's not that people really, really care exactly how fast the universe is expanding today. Obviously, that's important, but we don't care about the precise number too much. What matters are these implications that it could be telling us something fundamental about the composition of the universe.
So, Andrew, if you were going to put your money where your mouth is, where would you bet?
Well, first of all, I would really much rather not bet on this because the jury is very much out. We know very little, honestly, about dark energy. So there's certainly room for us to be wrong about how dark energy is behaving. On the other hand, we do have an awful lot of observations locking together to show us what dark energy is doing. And so my personal feeling is it's probably less likely to be a problem with dark energy and more likely to be either something that we haven't understood about stars or something about the early universe, some kind of missing particle.
It's my hope that this teaches us something about the universe. That's my goal.
The thing that most excites a scientist, or at least me, is if there's clear evidence that there's something we don't understand, because that provides a puzzle, and we all love to solve puzzles. So that's essentially what this is all about.
For now, we're left with more questions than answers. But that's an exciting place to be. These moments of confusion and controversy, these are the moments when a big breakthrough seems like it's just round the corner.
Whatever the result, it's clear we're entering a new, exciting age of discovery.
The telescope, built from the hard materials of this Earth, becomes lost in the immensity of space. Every new telescope creates more problems than it solves.
We're not on air next month, but we're back in April. Until then, good night.
The BBC Sky at Night Book of the Moon, a guide to our closest neighbour, is available now. Coming up, the ENO's remarkable staging of a masterpiece, Britain's War Requiem, part of our classical century season. Next.